Our world revolves around electricity. We cannot imagine a world without electric current. Electric current is a flow of electrons. Electrons travel in an electric conductor, which in most cases will be a wire. What happens when you bring a magnetic compass near a current carrying conductor? It deflects. What does it mean? That means that every current carrying conductor develops a magnetic field around it. This was first detected by Hans Christian Ørsted, and hence the unit of magnetic field strength is named Ørsted in his honor. A magnetic compass has a small bar magnet in it. So, when a compass is brought near a magnetic field, it deflects. The area around a magnet where another magnet feels the force of attraction or repulsion is called magnetic field. The lines in which iron filings align when brought near a magnet is known as magnetic field lines. Magnetic field lines have the following property. They start from North Pole and ends at the South Pole. They form a closed loop. The relative strength or field is shown by the degree of closeness of the field lines. No two lines are found to cross each other. We have seen that every current carrying conductor produces a magnetic field. But what if we change the polarity of the battery? Yes, if we change the polarity of the battery, the field lines also changes their direction. This can be detected by the magnetic compass, which now deflects in the other direction. Now let us see what happens to this magnetic field when the current is increased. We see that the deflection in the compass also increases. Now, keeping the current constant, move the compass away from the conductor. What happens now? We see that the deflection in the compass decreases as we move the compass away from the conductor. That is, the magnetic field is stronger near the conductor and get weakened as we move away from the conductor. How do we find the direction of magnetic field in a conductor? To do that, imagine as if you are holding the conductor in your right hand, such that the thumb points towards the direction of current. The fingers which are wrapped around should be the direction of field lines. This is known as right hand thumb rule. Suppose that a straight wire is bent in the form of a circular loop and a current is passed through them. How would the magnetic field lines look like? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. Similarly, at every point of a current carrying circular loop, the concentric circles represents the magnetic field lines around it. It would become larger and larger as we move away from it. By the time we reach at the center of the loop, the arcs are these big circles would appear as straight lines. A coil of many circular turns of insulated copper wire wrapped in the shape of a cylinder is called a solenoid. A solenoid produces a field around it that looks like a bar magnet. One point of the solenoid acts as a north pole and the other acts as a south pole. The field lines inside the solenoid are in the form of parallel lines, and therefore the field inside a solenoid is a constant. We already know that a current carrying conductor produces a magnetic field. So suppose we keep a magnet near a conductor. What might happen? Yes, the conductor will exert a force on the magnet, and the magnet will exert an equal and opposite force on the conductor, and this makes the conductor move. An electric current flowing through a conductor produces a magnetic field. The field so produces exerts a force on the magnet placed in the vicinity of a conductor. French scientist Ampere suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. The displacement of the rod suggests that a force acts on it when placed in the magnetic field. The direction of force is reversed when the direction of the current through the conductor is reversed. Again, if the direction of the field changes, the force acting on the rod reverses its direction. Hence, we conclude that the direction of force depends upon direction of current and direction of magnetic field. The direction of current, magnetic field and force can be illustrated through a simple rule called Fleming's left-hand rule. According to the rule, stretch the thumb, forefinger and middle finger of your left hand so that they are mutually perpendicular. The forefinger shows the direction of field, middle finger current, thumb the direction of motion of force acting on the conductor. Electric motor is a rotating device which converts electrical energy to mechanical energy. They are important components in electric fan, refrigerators, computers, etc. It consists of magnet, rectangular coil and a battery. The current flowing through the parallel arms of the rectangular coil are opposite. Hence they experience forces in opposite direction which turns the coil. Using Fleming's left-hand rule, it's clear that arm CD will experience a force in downward direction while AB will have a force in the upward direction. As the motor completes half rotation, the forces in the arms are in the same direction. The motor rotates back to its initial position. To avoid this, split rings are connected to the battery which maintains the current in the left arm in upward and right arm in the downward direction. Since the direction of current is not changing in the arm, the motor will rotate in the same direction. Now let us imagine a situation in which a conductor is moving inside a magnetic field or a magnetic field is changing around a fixed conductor. This was first studied by English physicist Michael Faraday in 1831. Faraday conducted an experiment in which he used magnet and a coil connected to a galvanometer. Initially, when the magnet is at rest, there is no deflection to the galvanometer. Now, as the magnet is moved towards the coil, the needle of the galvanometer deflects in one direction, and when it moves away from the coil, the deflection is opposite. When the magnet is kept stationary relative to the coil, the deflection of the galvanometer drops to zero. This is clear that now, as the magnet is moved towards the coil, the needle of the galvanometer deflects in one direction, and when it moves away from the coil, the deflection is opposite. When the magnet is kept stationary relative to the coil, the deflection of the galvanometer drops to zero. Thus, it is clear that motion of the magnet with respect to the coil produces an induced potential difference which sets up an induced current in the circuit. An electrical generator is a device used to convert mechanical energy to electrical energy by rotating a conductor in magnetic field. It consists of a rectangular coil placed between two permanent magnets, and the ends of the coil are connected to two rings. When the axle rotates in the magnetic field produced by the permanent magnet, an induced current sets up in the coil. After a half rotation, the direction of induced current in the coil changes. Thus, after every half rotation, the polarity of the current in the arms changes. Such a current, which changes direction after equal intervals of time, is called alternating current. This device is called an AC generator. The supply from which we receive the current to our houses is called as mains. The mains are connected to the supply meter from which they are connected to the wires of the house. The electrical appliances with metallic or high conducting exteriors accumulate static charges over time. If a neutral body comes in contact with the exterior of such object, they lose their charge. So if we touch such object, we get an electric shock. To avoid this, a third wire called as ground is taken from the object and the other end is connected to a large object like the earth. Earth, being so large, can absorb large quantity of charge, thus making the exterior of the object neutral and safe. Electrical appliances are connected from the mains in parallel. This ensures that all of them receive the same voltage. One of the measures done to improvise the safety of the circuit is the usage of fuse. The fuse is a thin conducting wire usually enclosed in porcelain. The fuse is connected between the mains and the electrical components. If a very high powered current tries to pass through the fuse wire gets heated and eventually melts and breaks itself, thereby breaking the passage of high power current through the electrical appliances which would otherwise get damaged.